All right, chapter 6 is going to be about the shape of molecules. So in this chapter, we're going to talk about how to draw Lewis structures. Like if you're given a formula, that tells you information about how many atoms you have in a molecule, but it doesn't tell you about the structure of the molecule. And the structure tells you a lot of information. It gives you a lot of properties about the molecule. All right, so that's really kind of what 6.1 and 6.2 are going to be about. 6.3 is this concept called resonance. Um, and 6.4, we'll talk about the shapes. There are actually names to the shapes. And there's bond angles, so we'll go a little bit more into it. Then 6.5, electronegativity and bond polarity. Again, it gives us more information. And once we understand that information, we can go into intermolecular forces, which are different types of forces that molecules have towards each other that affect the melting point and the boiling point of molecules. All right, so the first thing I want to talk about is drawing structures, Lewis structures. Okay, so the first thing to remember is that atoms obey this octet rule. We've talked about that several times, where atoms gain and lose electrons until they are isoelectronic with their closest noble gas. All right, and mostly the structures we're going to be talking about when we talk about Lewis structures are covalent bonds. All right, so nonmetals. These are all nonmetals bonded to each other. Ionic compounds are just plus and minus charges. There really aren't that many structures we're going to talk about in this class. Mostly it's with all the nonmetals. Okay, but the important thing is the octet rule. And this is kind of showing you an example of a chlorine. So imagine you have a chlorine bonded to another chlorine. These are covalent bonds. The bond that is between the two chlorines is a covalent bond. And if you remember from the previous chapters, covalent bond means sharing electrons, shared. All right. So how do you know this is octet? Well, if you look at this chlorine, we have 2 electrons here. This chlorine has another 2 electrons. Remember, these are called lone pairs. There's another 2 electrons, so that's 6 electrons. But then you got to remember, every bond is 2 electrons. 1 electron here, 1 electron here. This chlorine supplies one of them. This chlorine supplies the other electron. So they are sharing the electrons. So this chlorine here gets these 2. And this electron here, this chlorine here also gets these 2. So they're sharing them. So the chlorine, each chlorine has 2, 4, 6 plus another 2 from what it's sharing, and that's what gives you the octet. Same for the other chlorine, 2 here, 2 here, 2 here, and then the 2 for sharing for the octet. All right, now everything is octet with the exception of hydrogen. So for example, if you have water, let's take water as an example. Water looks like this molecule. All right, and remember, everything is octet with the exception of hydrogen. So this would be the Lewis structure. Hydrogen, each hydrogen has just this bond, which is 2 electrons. This hydrogen right here has this bond for 2 electrons. But the oxygen has 2 here, 2 here, 2 in this bond, and 2 in this bond for a total of 8. All right, so every atom, with the exception of hydrogen, will have octet, and hydrogen will have 8. Hydrogen will never have lone pairs. Never lone pairs. The reason is because it only wants 2 and it's got to make a bond, so the bond is the 2. All right, so this will come up again as we start doing these. It'll make sense. Okay, so let's talk about how to draw Lewis structures. Now, the way I'm going to teach you is different than how the book kind of teaches you. They teach you the same way, but they teach it to you in a different order. I don't like how the book does it. I've been teaching this way for 15 years. No one's ever had a problem. It's a very linear way to do it. If you follow these rules and steps, you will always get the correct structure. All right. The first thing to remember is that there are 2 goals. There are always 2 goals when drawing Lewis structures, and both of these goals must be met in order to have the correct structure. Okay, so there are 2 goals. The 2 goals are: 1, you must account for all valence electrons, no more, no less. Once I start going over the rules, this will make sense. But for example, if your molecule, if you calculated 18 valence electrons, your final structure has to have 18 valence electrons. It can't have 20, can't have 16. I will remind you of these rules as we do them. Okay. The other thing is that everything must be octet. So your molecule at the end must be octet with the exception of hydrogen, of course, which only has 2 electrons. So both of these rules must be accounted for. If you do not account for both of these rules, you will not have the correct structure. All right. So let's go over the rules. There are 5 of them. Now, it doesn't mean you necessarily have to do all 5 of them, And this is the order that you must do it in. If you do it in any other order, you will get it incorrect. All right. The first one is to determine the valence electrons. If there is a positive charge on your molecule, you're going to subtract electrons. All right. If there is a negative, you are going to add electrons. All right. So for example, let's take like NO3 with a minus charge. When you figure out the valence electrons, you look at how many valence electrons each atom had. All right. Remember how we do it is by looking at the group number that they're in. So nitrogen is in group 5, so nitrogen has 5 valence electrons. All right. Oxygen is in group 6, and there are 3 of them. So we are going to add 3 6s. And since I have a -1 charge, I'm going to add 1. All right, remember, negative means you're adding electrons, positive means you subtract. So when I add all these up, I get 24 valence electrons. This is how you do it for every molecule. Okay, so 5 plus 6 plus 6 plus 6 plus 1 equals 24. All right, let's say we have like an NH4 plus 1 charge. Nitrogen has 5. Hydrogen is 1, but I have 4 of them, so that's 4. And since I have a plus 1, I'm going to subtract 1. So this will have 8 valence electrons. Okay, that's all you need to do for step 1. This number becomes important because once you start putting your structure together, my final structure must have 24 valence electrons. All right, like I said, I will show you how to do all this with an example once we go through the rules. The next rule is to draw a skeletal structure for a central atom and all other atoms around it. All right. Here are some guidelines. Hydrogen and fluorine are never the central atom. So like if you have H2O, all right, obviously oxygen has to be the central atom because hydrogen will never be the central atom. Okay. Step 2, oxygen rarely is a central atom unless it has to be. Like water is a perfect example. Oxygen has to be because hydrogen never will be. All right. Ozone is O3. Well, obviously oxygen has to be our central atom. There's no other choice. Okay, but if we have like NO3 minus, what's going to be our central atom? It's going to be nitrogen. All right, with oxygens all around it. Okay, so I'm going to use the NO3 as kind of our example. All right, number 3, put maximum number of electrons on outer atoms until octet. Okay, so now you have the NO3, you put the maximum electrons on your outer atoms only. All right, so it usually means 3 lone pairs because you need this to be an octet. So we're going to put 3 lone pairs there. Notice this is 8 now. 2, 4, 6, and then the 2 in here is 8. All right, there's another 8 here, and there is another 8 here. Okay, so that's step 3. Just put the number of electrons on the outermost atom. Okay, now step 4 is any remaining electrons go on the central atom as lone pairs. Okay, so how do I know if there's any remaining? Well, I got to calculate how many I currently have used and compare it to how many I need. So if you do this, 8 and 8 and 8 is 24 valence electrons. Well, I have accounted for all 24. So I do not do step 4 for this molecule because if I put 2 lone pairs on my central atom, I would now have 26 electrons, and that is not one of the goals. One of the goals is I have to count for 24, no more, no less. So I am done. So I don't do anything for step 4. Step 5 now is if your central atom is not octet, because remember the goal is account for your 24 valence electrons and everything must be octet. So if after step 4 everything is not octet, you make it octet by making a coordinate covalent bond. This is a double or triple bond. What a coordinate covalent bond is where you take a lone pair, so a lone pair becomes a bond. That's basically in like the simplest form what a coordinate covalent bond is. So I'm going to take one of these lone pairs. Let me redraw this nitro over here. So this is where we're at so far. I don't have any remaining, so I skip step 4 because it does not apply. But notice my nitrogen is not octet. I have 2 here, 2 here, and 2 here for 6. So I need to make a coordinate covalent bond. So what you do is you erase one of the lone pairs, and wherever you erased it, you make it into a bond. That's what step 5 is. Now, you can use any lone pair you want. If you wanted to, you could have erased these and made the double bond there. or you could have erased these and made the double bond there. It doesn't matter. They're all the same. This is what resonance is, and this is what we'll talk about when we get to, I think, section 6.3. All right, so now if we go through everything, this oxygen has 8, this oxygen has 8, this oxygen has 2, 4, plus 2 here and 2 here has 8, and then our nitrogen has 2, 4, 6, 8. So I've met both goals. I've accounted for 24 electrons, and everything is octet. So this would be the Lewis structure of NO3 minus. Okay, on the next few pages, I want to go over a few other examples just to kind of make sure you understand how to do this. Okay, so here we go. We're going to do 3 examples and kind of show you how all these rules apply. All right, we're going to do SO2, we're going to do SO3, and then we're going to do SO4 with a 2 minus charge. All right, so remember the first step is valence electrons. Okay, so let's calculate the valence electrons for each example. So sulfur is in group 6. All right, so there's 6 valence electron. Oxygen is also in group 6, and I have 2 of them, so that gives me 12. So there are 18 valence electrons for SO2. Okay, why don't you do the same for SO3 and SO4 2 minus? Put it on pause and come back, and we'll do it together. All right, welcome back. So sulfur has, if you didn't do it, pause it right now and do it. But sulfur has 6. Each oxygen has 6 for 18. So this is 24 valence electrons. And then in the SO4 2 minus case, sulfur is 6. Each oxygen is 6 for 24. And then the minus 2, I add another 2. And I believe this equals 32 valence electrons. So 18, 24, and 32. So remember, at the end, I have to account for all of those. Okay, so now step 2, I'm going to write down the valence electrons so that we keep track of everything. The next step, step 2, is you draw the skeletal structure. Okay, so remember, this is SO2, this is SO3, and this is SO4 with a 2 minus. So sulfur is the central atom, because remember, oxygen rarely is unless it has to be. So that's pretty simple. SO3 has 3 oxygens, pretty simple, and SO4 has 4 oxygens. All right, so all I'm doing each page, I'm going by a new rule, okay? So the next one, again, this is 18 valence electrons, SO2, 20, nope, not 18, yeah, 18, oh, that's right, I'm sorry. 24 for SO3, and 32 for SO4 2 minus. I have my skeletal structure. All right, that was step 2. Step 3 now is to put any remaining, or I'm sorry, to put maximum electrons on the outer atoms only. So that means it's going to be basically 3 lone pairs. All right, unless it's a hydrogen, then you put nothing, because hydrogen only wants 2. So, and why is it 3 lone pairs? Because I need to make it into an octet. And this is making all of these oxygens into an octet, because it already has 2 electrons from the bond. All right, each oxygen is bonded to the sulfur for 2 electrons, and then we're putting in 3 more lone pairs, which is another 6. So now everything is octet. This is octet. Only my outer atoms are octet. My central atom might be octet, it might not be octet. We have to go to the next rule. The next rule is any remaining electrons go on the central atom as lone pairs. Okay, so this is 18. All right, I have 8 here and 8 here for 16. There are 2 electrons remaining, so it goes as lone pairs on my central atom. Now, I stop once I get to 18. So I now currently have 18 electrons on here, so I am done. I know you might be thinking, well, the sulfur's not octet. Well, this is going to be step 5. Step 5 is going to be make the covalent bond in this case. All right, in this case, I have 8, 8, and 8. I have 24. Well, guess what? I don't put any on my central atom because I am done. I have 24. And in this case, 8 times 4 is 32. I have accounted for all 32 valence electrons. So I am done. So really the only one that I needed to put that on was that one. All right, so now the next rule is if your central atom is not octet, what do? You make it octet by making a coordinate covalent bond. So in this case, my sulfur is not octet, so I have to erase one of these lone pairs, and I make it into a double bond, so I'm sharing the electrons with sulfur. Same thing here. Notice sulfur is not octet. Choose whichever ones you want. I'm going to choose those. It doesn't matter because we'll talk about resonance in a second. And now my sulfur is octet. 2 here, 2 here, 2 here, and 2 here, octet. And notice I still have 24 valence electrons. I haven't changed. 8 here, 8 here, and 8 here. Same thing here. My sulfur is 2, 4, 6, 8. This oxygen is 8, 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. Over here, I'm done. I don't have to do anything. My sulfur is octet, my oxygens are octet. I've accounted for 32. So these are the structures for your molecules. Okay? If you follow all 5 rules, so let's go over the 5 rules again. Number 1, you have to do your valence electron count. Number 2, skeletal structure. All right? Number 3, maximum electrons on outer atom. I'm doing kind of the Cliff version of this. Number 4, any remaining. All right, lone pairs on central atom. And then number 5, if not octet, make coordinate covalent bonds. Coordinate covalent bonds. All right, so for practice, do the Lewis structure of, let's say, NO2 minus and do PO3 3 minus. Put this on pause, come back, we'll go over the Lewis structures. Welcome back. Let me make that P a little bit nicer. I hope you had time to do it. If not, start off and do it. Okay, nitrogen. So let's go over these. Nitrogen. So valence electrons. Nitrogen is 5 plus each oxygen is 6. So that's 12, so that's 17 plus 1, 18. All right? So nitrogen is 5, each oxygen is 6, so it's 12 plus 1 gives me 18. Phosphorus is 5, each oxygen is 6, so that's 18. And then I'm going to add 3, so that's 26. All right? So the NO2, nitrogen is my central, oxygen's around it. Put on maximum electrons. Okay? So that is how many? 8? That's 16. Any remaining as lone pairs. So that's my 18. And I have to make a coordinate covalent bond because I don't. So there you go. That's the structure of NO2. PO3, phosphorus, oxygens on the outside, maximum electrons on the outer atoms. And that is, let's see, that's 24 because 8 times 3, there's 8 here, 8 here, 8 here, 24, 25, 26, since I need to get 26. Everything is octet. I am all done. So basically, I stop at number 4 on this one, rule 4. This one, I stop at rule 5. Okay? So hopefully this makes sense. Practice it. There are practice problems that you can do so that you have a good sense of how to do these. All right? This is just to kind of give you the wordage again that we've talked about. You have lone pairs, you have bonded pairs. They call them terminal atoms. I've been calling them outer atoms. It doesn't matter which term you use, outer or whatever. Oh, sorry. And then you have your central atom. All right? Here's some more practice problems. Why don't you practice them, and when you come back, we can look at the answers. Welcome back. Hopefully you went through all the rules. I guess I didn't put the answers down here, so let me do that. So selenium, there are 6 valence electrons. Each bromine has a total of 7, so that's 14. So we have 20. So we have selenium with bromine. All right, and then you have your maximum electrons, 16, 17, 18, 19, 20. That's the final structure. You might be saying, well, how did I know selenium is the central atom? That's a good question. There's no oxygens or anything to kind of guide you. Usually, not all the time, but the first atom that's usually written is your central atom, or the one where there's only one of them. All right, it's kind of obvious, like this is going to be the central and the 3 chlorines are around it. All right, that's kind of how you know. If it didn't obey one of the rules we talked about, most cases it does, but it doesn't always have to. But usually the first atom that's written or the single atom is usually the central atom, okay? So H3O, oxygen. So first of all, hydrogen, there's 1, so there's 3. I'm sorry, hydrogen has 1 valence electron. There's 3 of them, so that's 3. Plus your oxygen is 6. And in this case, I'm going to subtract 1. This is the first time we see a subtraction, so that's 8. Oxygen's my central, because remember, hydrogen is never your central. All right, we don't put any electrons on the hydrogen because they are done with the duet. I'm sorry, with 2. It's called the duet rule, by the way. Octet rule, duet rule. So any remaining central atom, so there's my 8, and that would be the final structure of H3O+. And then PCl3, all right, phosphorus is 5, each chlorine is 7 for 21, so it's 26. So phosphorus plus chlorine, and then phosphorus plus another chlorine. So that's 24, 25, 26. All right, hopefully this makes sense and you got it. And if there's any questions, obviously, please come and talk to me. We're going to put on pause right here and we will start section 6.2 on the next video.